Good day, everyone. My name is Berkenda. I'm the Director of Operations and Strategic Projects here at OmniAir Consortium. I know that many of you I frequently see at our working groups, monthly meetings, and of course at PlugFest, which we have coming up. But for those we've not met, OmniAir is a leading industry association promoting interoperability and certification for connected vehicles, ITS, and transportation payment systems. Our members include connected vehicle, ITS and road tolling technology device manufacturers, ITS deployers, testing laboratories, and other stakeholders, all promoting the proliferation of certified interoperable devices. For nearly a decade, we have provided the opportunity for members to work collaboratively to develop and determine the requirements for national certification programs. Our members have the opportunity to shape the future of ITS and IoT technologies and to work with industry leaders and transportation professionals to accelerate their interoperability. Before we get started, I have just one housekeeping reminder. Questions are definitely encouraged. We will have time for Q&A with our guest presenter near the end of the presentation. However, you may submit questions in the questions box as they come to mind. You don't have to wait until the end. With that, it is my pleasure to introduce to you today's guest presenter, Lei Sun. Lei, if you can go ahead and pop on with us. Before I turn this over to him, I'd like to share a bit about his background. Lei Sun is a senior staff software engineer at Qualcomm. He is working on V2X related system software design development. Prior to joining Qualcomm, he worked at Sierra Wireless Incorporated, where he led the software architecture team in automotive BU and helped the organization secure $500 million in business with a major automotive manufacturer. He has 22 years of software system experience in the area of broadband networking, satellite communication, and embedded software development in semiconductor sectors. Lei earned a Master of Science degree in aerospace engineering from University of Central Florida. Well, Lei, thank you so much for joining us today. The floor is yours.
Thank you, Berkenda. Good morning, everybody. In today's presentation, we're gonna go over the topics of running TCP over CV2X and PC5 interface. Okay, so the presentation is organized in this order. First, we're gonna review some background, and then we're gonna start with looking at the global IPv6 support over PC5, and then we're gonna review the IEEE 16093 message format, and then followed by discussing what the ITS stack needs to do in order to support its features, and then we also take a look at the difference between the CV2X versus DSRC when running TCP over it. And the next topic, we also discuss how to run TCP if you don't have the global IPv6, if you only have like the local IPv6 support. And similarly, we also need to know what the ITS stack needs to do in this case. Okay, and then followed by, we're gonna share some resources that's available, pointing to some sample application that implement this feature. And then we're also going to review some existing IPv6 test case from OmniAir. And at last, we're going to present some simulation that we performed to discuss what's the impact it's going to be if you're running TCP. What's the impact for BSNM looks like. Okay, moving on. Okay, so we all know that the CV2X is designed for vehicle safety critical message like a V2A and V2I applications. But in North America, there are some use cases. For example, certificate download, third top off, misbehavior reporting, and probe data upload from the OBU to RSU. So, but you can always argue that for CV2X, particularly LTE V2X, you always have the WAN connection available, the LTE data call available. You can certainly do that, but there are some concerns, like for example, for LTE data call, there are associated costs with it, and other cases like standalone V2X, which you don't have the WAN connection available. So in this case, so running TCP over IPv6 over CV2X has its advantage. Okay, so fortunately, IEEE 1609.3 define some messages for this use case. The message called the WRA, Wave Router Advertisement. That is to provide information about the infrastructure, network and connectivity. So the receiving device should be able to use that message to configure and participate in the IPv6 network. But this 9.3 is originated for DSRC. But the CV2X and DSRC on the radio is different, but this higher level message it doesn't have related to the radio, so it can be used by CV2X as well. Okay, and then so some early deployed RSU OPU may only support link local IP, but even in that case, there is an approach that we call a proxy approach, that we have proxy program running inside RSU that can relay the packet back and forth between the OPU and the remote server side. And so for both cases, Qualcomm has developed a sample application that demonstrates how to use and implement this. Okay, our first topic, how do we run TCP over PC5 with the, in the case of you do have global IPv6 address. So this is the topology, that the application use case that we talk about. As you can see on the left side, this is the cloud, the server that can be accessed from the OPU. And in the middle is the RSU, and the right part is the OPU. So the RSU is going to periodically broadcasting WRA message, routing advertisement message, and the message can contain some information that we're going to cover in the next slide. When the OPU receives this message, it start configure its own IP address, and then after IP address has been configured successfully, it can establish the connection with the remote server, just like any other internet devices can do. Okay, you open up a circuit, then you connect to the server. Okay. Okay, now let's take a look at the how the WRA message looks like. This is a part of the 1609.3 spec. There are like 6 fields defined in the message. Router lifetime, it's the first one, and it basically tells you, how long your router can support this IPv6 configuration. And then it comes the IP prefix, and then the prefix length, and default gateway, primary DNS, and optionally you have the wave information element extension. Okay, so these are some of the fields. For example, the wave extension is optional, but the most important one, the IP prefix and IP prefix length, are the one that you definitely should have, because the purpose is to configure, to tell the OPU what IP you need to use. Okay. Okay, now look at the detail of how the IPv6 address is composed. So as I said, you have the IP prefix and the prefix length. Typically, it's a 64-bit prefix, and for example, that I listed in this slides. And then in order to compose the 128 bits full IPv6 address, there comes 40 bits random value. And then at the end is the 3 bytes, 24 bits L2 address of the CV2X. Okay, so this is how the entire 128 bits IPv6 address is composed after receiving the WRA message and taking the prefix plus the 40 bits plus 24 bits. And together they come the entire IPv6 address. Okay, so in order to support this, what does ITS stack need to do? On the RSU side, because the CV2X, the L2 address will periodic updates for randomization. So on the RSU, IT stack need to obviously track the L2 address update and build the wave router advertisement message with the pre-configured prefix length, etc. And then the RCU is gonna encode and sign and broadcast the double message periodically. The periodicity is implementation defined. And of course, because in this case, you are using RCU as the router to access the internet. So it has to support the routing rules for OBU to be able to connect outside. On the OBU side, so obviously it's going to receive your broadcasted double message and verify the authenticity. And the scenario is that in the case that you are in the multiple RCU range, that you could receive a multiple. You could receive WRA message from multiple RCU. In this case, you need to decide which one you need to pick and which one you're going to associate with. So the association can be based on PSID, distance, RSSI, or etc. and different criteria. It's implementation defined. And the point is, ultimately, you only should pick one and make association with that RSU at one time. Okay. And another action that the OPU need to take care is this association, meaning you invalidate your IPv6 global address after you finish your operation. This association can happen when you go out of range, or when if the router lifetime is specified in the WR message, and your router lifetime expired, then you could take the action of this associated with the RSU. And optionally, if you're driving along the road, you can optionally implement logic handle translation from one RSU to another to keep your TCP session continuous all the time. Okay. Okay, so there are additional requirements because I want to mention this because in our example application, there are some like implementation defined behavior. For example, for CV2X, there is this flow concept. The flow means like for different traffic. For example, the basic safety message BSM, there are specific periodicity, specific priority. So we call this a flow. But TCP traffic, obviously, it's another type of traffic. It's different flow. So the implementation defined here is that for CV2X traffic, there should always be a flow associated with it. That means the IT stack for TCP traffic, you need to create a flow for TCP traffic because the TCP should have a distinct priority level, PPPP level, and maybe a different PDB value as well. So this is a special case for the CV2X use case, CV2X application, if we run a TCP on top of it. In the later slides, we have the our sample application in Tele SDK that you can find out that it's handling this case. Okay, moving on. So okay, now let's take a look at what's the difference between CV2X and the legacy DSRC from the TCP perspective. Okay, for legacy DSRC, it's a multi-channel operation. So you have the CCH, SCH with time division, and the WRA message running on a dedicated CCH channel, and the vehicle safety message like BSM running on another safety channel, and the non-safety application, in this case is TCP, run a separate channel. Okay, so and also DSRC has a 42-bit L2 MAC address rather than 3 bytes, 24 bits in CV2X case. However, for if we run TCP over CV2X, they share the same channel. I mean, the safety message, vehicle safety message and the TCP, they run on the same channel. And so there is a requirement here that because TCP is not safety critical, so we must ensure that the safety message takes priority. So the TCP transmission would not cause any blocking of the vehicle safety message. So this can be achieved by two mechanisms. The first one is that we assign this TCP flow, IPv6 flow, with lowest PPPP level 8. Okay, and another approach is that we apply the SAE J3161/0 profile that handles the mapping of the flow to the CR limit. For example, if your PPPP level is 8, so the mapping example is below. When the channel busy rate is less than 30%, we limit the CR to be like 4% only. So by doing this, we ensure that the TCP will never occupy, a significant amount of the available radio resources. Okay, so this is the solution that we make sure that, if running TCP over V2X, PSM vehicle message always precedes the TCP traffic. Okay, now the next section. What do we do if you don't have the link global IP and you only have link local IPv6 address available? Okay, so why is this case? Because in some earlier CV2X product, there is no significant use case of that we have to support like a global IP over PC5. So the early deployed product doesn't support the global IP, only link local. And as I mentioned in the beginning of the presentation, the LTE V2X, because you almost always have the LTE data path available to the internet. But even you don't have a global IP, it's still possible for OBU to access the cloud by the suggested approach that in the flowing thread. Okay, because in this case, you don't have global IP, so the OBU can only communicate with the RSU through the link local. But could be a proxy program in the RSU that relay the packet between OBU and the internet server. So the suggested approach is that the RSU still broadcasting this WSA messages, but in the message you incorporate, your supported internet destination server and make association with the PSID in the WSA. Oh, this, by the way, this is WSA with service advertisement, not with router advertisement in this case. Okay, so the suggested approach is that you broadcast this kind of message, and inside the message you put the information inside. For example, what's the supported server IP, what's the PSID, and may even contain what's the port number, things like that. Okay, and then the OBU, once receive this WSA, it decode it, and then it can using the specific port to access using the specific port and the server address, and send this connection request to the RSU, and the RSU relay this packet to the designated server, and in bidirectionally relay this packet. So that's in this way, you achieve the purpose of accessing internet without using global IPv6 address. Okay. Okay, again, similarly, in this case, in link local case, what does the ITS stack need to do? Okay. Similarly, similar issue, the flow concept that we talked about. In this, because you're always going through CV2X, so you always have the flow associated with the TCP traffic. So you also need to take care of this flow creation issue. Okay, and the other is pretty similar, the same, because you're running TCP, you don't want to cause any block of the safety message. So your TCP traffic should also be assigned with PPPP level 8, and also applying 3161/0 profile to limit the TCP traffic by using the CR limit approach. Okay, that's the same requirement for ITS stack. Moving on. Okay, here we, as I said, there are some reference resource available for both the link local and global IP, IPv6 over PC5 case. One example I would like to mention is our reference ITS stack. It's called the rates of kits. This is functioning as a full ITS stack, which can send and receive BSM messages, and also handling encoding decoding of WRA messages. And it also take care of the simulator as RSU and OBU. For OBU, it receive your broadcasted WRA and making API call to establish the IP address. Also create the flow automatically, and then after that you can start using standard TCP application to access the remote server. The standard TCP application can be like something like a wget or whatever. We also have some application note document available to describe how to run the link local IP address case. Okay, if you don't have the global IP. And for this link local, there is also a sample program available that in the code or source code. Okay, so so for OmniAir existing test case, we run through some analysis for when it comes to the related to IPv6 testing. Most of the test case still applicable for PC5 case, but there are a few that probably need to be revised. For example, I'm not sure if you can see my cursor, but the third line, the red line, IoT reset link local IPv6 address to a specific value. That does not really apply for CV2X because CV2X, if you recall the previous slide, the IP address formed by some random bit value. So once you reset, it can only reset to another random bit value instead of reset to a specific value. Okay, that's one test case. Need to be revised probably. Another test case for this that need to be revised is the highlighted here in red, that the ping. In the CV2X TCP case, ping is not really supported. Okay, so rather than using ping, you can invoke any other TCP application instead, like iPerf, to verify the connectivity. Okay. Okay, another important issue that we want to discuss is that although we impose the CR limit by using 3161/0 profile, and we set the proper PPPP level to be the lowest one, but what we still need to consider what would be the impact of the running TCP over BSM, particularly when, let's say you are in a scenario when the the CR limit is approached to the 4% boundary, because we know over 4%, the TCP traffic will be completely blocked, because about 4%, the CR limit is set to be 0. So there's no redo resource allocated for TCP. But if we're below that, but in the boundary, what's going to happen? So we still need to analyze that. So we perform some simulation to see what would be the impact of this case. So the simulation is performed in the following setup. It's a freeway scenario, 3-lane 2-direction traffics. So the RSUs 20 dBm conducted power, and same thing for the OPU, 20 dB conducted power. Again, the CR limit is 4% for PPPP equal 8. CPR is about 30%. The condition is we simulate the scenario when it's in the boundary, in the highest boundary of the channel base rate. Okay, and the speed is 60 kilometer per hour, and inter RSU distance 1 kilometer. This is the simulation scenario is that we have like 4 RSU, each one has a 1 kilometer distance. Okay, so and the KPI here we want to measure is the packet reception ratio and inter-packet gap, IPG. Okay. So what kind of traffic are we running during the simulation? We run BSM, obviously, for sure. It's 190 bytes packet followed by 300 byte packets, 10 Hz transmission rate. And for BSM, the priority is higher, PPPP level equal 5. And we also run TCP with the 1500 bytes length. It's the MTU of the TCP. The TCP direction is uploading, meaning we are sending data from OBU to RSU. It's like the probe data uploading case. And for TCP, PPPP level is 8, and one-shot transmission. Now there are two numbers that we use to different describe situation. The X% vehicle transmit traffic at the rate of Y transmission per 100 milliseconds. That means we are simulating 50 vehicles. So at any given time, we have X%. If the X equal 5, there's like X equal 10, for example, you have like 5 vehicles transmitting TCP at any given time. And the rate of transmission is like a Y transmission per 100 milliseconds. The reason we use Y 100 milliseconds is because the BSM is transmitting using 10 Hz. So every 100 milliseconds, there's a BSM transmit. So we use this 100 millisecond Y transmission per 100 millisecond to see how the resource is allocated and what would be the impact. Okay, and then for the RSU traffic, because we're simulating the upload case, so the RSU is doing sending the TCP-ACK. If you look from TCP point of view, so it's 800 bytes packets because the RSU can handle like a multiple TCP connection, and the transmission rate is 20 Hz. Again, for PPP for TCP, the RSU traffic is sending back setting the PPPP to be 8. Okay. So here's the simulation result. So we simulate the vehicle density is the 50 vehicle per kilometer. So that in this range, only 1 RCU in this 1 kilometer. So you have 50 vehicle in 1 kilometer. Okay. So the previous X and Y parameter in this page is showing as X equals 10%, Y equals 2 transmission per 100 milliseconds. So meaning at any given time, there is only 5 vehicles doing the TCP transmission. Okay, and the rate is 2 transmission per 100 milliseconds. Okay, so I will not go through this detail in this table, but the result of this scenario is that when the packet reception rate is 90%, the net effect is that with the TCP is that the BSM range is decreased by 12% from 250 meter to 220 meter because of the TCP traffic. Okay, this is one scenario. And in the next slide, everything is the same except this X parameter changed from 10% to 5%. Okay. So that means at any given time you have less vehicle. You have like a 2.5 vehicle transmitting TCP. So as you can see, the result is in this case, the range of the BSM decreased by 8% from 250 meter to 230 meter because of TCP traffic. If we look at the previous one, when the X is 10%, so the PR decreased from 250 meter to 220 meter, as opposed to 250 meter to 230 meter. So this is the expected result because obviously when you have less vehicle transmitting TCP, you occupy less radio resources. So the impact of BSM will be reduced because you have less vehicle introducing the TCP traffic. Okay, so this is the result of running simulation. For this topic, we also performed the lab test, the bench test, and also field test, and the rack test. But the result will be shared in a separate event that for the same topics as you running TCP over PC5. Okay. And we also, by the way, we also measure the performance data of the TCP, separately from to see how the TCP impact the BSM. We also run the TCP performance alone to see how what the bit rate you can get. How many data you can transfer during your TCP connection period. Again, the result will be shared in separate event, but here I want to touch base of the theoretical performance that we calculated. So it's you can imagine there are a lot of parameters that can affect the performance. For example, PPPP level, right? That's one thing, because if you have higher priority, you can even preempt BSM. So you have TCP can occupy more radio resources. So, and then the MTU size of the interface and the modulation scheme, for example, the release 14/16 QCOM versus release 15/64 QCOM, the higher modulation, you probably have a higher throughput performance. And also the radio resource configuration parameter, for example, the CR limit, TX exclusion mechanism, and RSRP thresholds. So all these can contribute to the performance of the TCP. But in our calculation, we limited to the following condition. Okay, because obviously you cannot change the PPPP because you don't want to preempt the BSM, right? So we impose some condition like below. So the MTU size is 1500 bytes. This is aligned to the simulation that we did before. And the modulation scheme, we limited to use release 14/16 QCOM only plus HARC. And we also limit we also impose the CR limit by applying the 3161/0 profile. So the CR limit is 4%. And we only consider the single OBU. It's communicated with the single RCU at a time. So the traffic is always lowest priority traffic, PPPP equal 8. And so by imposing following condition, we did measurement and also theoretical calculation. So the throughput we can get is about 300 kilobytes per second for TCP. For the use case of, let's say, third top of things like that, it's capable of handling that, because if you're driving along the RCU, you probably have like 1 minute to pass through in the range, so you can download the pretty much the certificate already. Okay, so this concludes the presentation. Thank you very much. So I will handle it back to Berkanda for question and answer.
Yes, definitely. So joining us for Q&A, we have Sean Michoud, also from Qualcomm and an active member of several OmniAir working groups. Lei and Sean, I'm going to check in now and see if we have any questions. So I'll have both of you, if you guys can both turn on your video and unmute your audio. It looks like we do have a couple of questions. Hey, Sean, there he is. Let's see. Okay, so first let me stop sharing. Okay, so the first question I see here says, why is the OBU MAC address not being used to complete the IP version 6 address and using EUI64?
You want to take that, Lei? Because it essentially is, right? That's the layer 2 source
that
address.
Layer 2, yeah. But it's only, like I mentioned, it's only 3 bytes, so 24 bits. But you need the other 40 bits to complete. Yeah, that's why the 40 bits random value come into place.
Okay. Next question we have, and before I get to this next question, looks like we only have a couple questions, is if you guys do have any questions or if anything has come to mind, go ahead and type that into the Q&A now, and that way I'll see it and we won't close out too early. Okay, so other question I have is the TCP3 handshake remain the same with the addition of the flow requirement?
Yeah, I can take that question. Yes, after the flow creation, the TCP is remain the same. I mean, it's the standard TCP. You don't need to do any modification for your existing TCP application. It can run just as is. Okay.
Okay. Well, I don't see any more questions. Let's maybe hold for a couple seconds. If you have any, oh, here we have one. Thank you so much, Sue. I see you here in the chat. Do you think any modifications to the SAE standards are required to specify the attributes you described?
I'll take that one, Lei. I think no. Nothing. The main standard where we picked this up was in /0, where the key parameters for the CR limits and the CBR under which this all can operate, which is a pretty lightly loaded network only. Pick that up, but the general TCP that our existing standards like 2945/4 and /C cover for these TCP sessions never really got down into any of the radio details. They rely on that 609.3 standard, which was the one we all worked so hard to update a few years ago to have that annex for the PC5 parameters. To allow how to adapt this 24-bit instead of 48-bit and include the communication profiles for the CV2X radio parameters instead of, say, EDCA parameters in 609.3. So hopefully nothing comes to mind where we would have to do that for the global IPv6. However, if we were attempting to widely deploy anything with dedicated link local proxies, there we might want to reserve a PSID. So we could either do that directly with 1609 or through the SAE spec that dedicates which application. So in this case, it would be the link local IPv6 service for SCMS, say for specific SCMS function that would need a dedicated PSID to associate with that proxy.
Okay. Thank you, Sean. Looks like we have a couple more questions that just came in. So we have typical TCP applications like is wget and curl need an interface name to be specified to perform the TCP operation. Will a new network interface be introduced or will be used the same RMNet interface?
You know, I would say that the interface names, that's an operating system specific topic. So RMNet, that sounds like, you know, a Linux device driver interface name. That is one approach, but you know, you have CV2X implementations that don't necessarily involve Linux and don't necessarily involve RMNet. But for sure, like any IP network, whether it's DSRC or CV2X, firewall rules are critical. Fortunately, all of these applications are still initiated by the onboard unit. That's kind of a common thread here in the North American TCP world, that everything is based on the discovery of service IDs and IP routing availability through the roadside unit. The roadside unit critically needs to be firewalled as well to only allow the appropriate traffic and routes. But how that's done is operating system and implementation dependent. But absolutely, it's just like any network protocol. It's got to have firewalling, and interfaces need to be carefully locked down to prevent exploits and unintended consequences.
Okay, thank you. I'm looking to see.
Frank's got a big question here.
Frank's got a big question. There's one above that. Will the implemented TCP communication and CV2X be susceptible to common cyber attacks? That's a good question.
Yeah, I think that was essentially the question I was answering. That
okay.
It's the same.
Oh, that was when you were answering. Okay.
Yeah.
Perfect.
Yeah, that it's the same requirements, whether it was DSRC or CV2X, that your session, when it's established, has to anything that's listening for TCP connections, which in this case is still the server. So this would be a SCMS server, a traffic management center's probe data clearinghouse, or weather upload that the SAE spec uses. Those are really the only places where you're open and listening for connections. This OBU style, North American SAE style TCP sessions are all initiated by the OBU. So it's purely outbound TCP connections. And how those are secured is also left up to the IP or the application profile, what's needed there. But typically it's a TLS session that works the same, regardless of which mechanism we're using here, the link local proxy or the global IP address. All that is application and network layer.
Okay. Looks like we have a question from the next one is from Roher. It looks like an OBU with no active certificates to use might still be considered a high priority message. If an OBU is able to determine this, can it perform TCP traffic to the same level as BSMs?
Yeah, there's no need for BSM certs to participate in the IP session. One tricky thing might be it still has to have the trusted root certs to know whether to trust a particular roadside unit. That's not actually critical, because as long as the TLS session can be established with their SCMS to that device is expecting, then and establish that secure session, whether the wave router advertisement was inauthentic or not is a little less important. But yeah, the certs are not needed for cert top off. You just need to have it initially, you know, with the the root certs have to at least be there for the whatever the roadside unit is signing those wave service advertisements with.
Okay.
Good question, Roger.
Yeah, that was a good question. Next question is, hi there. There are a number of grant programs researching technologies that increase safety around construction zones. Do you see TCP communications over CV2X being used to other data flows that are not SAE J2735 or J3161 defined datagrams?
I'll take that unless you want to, Lei.
No, I don't.
I would say probably not.
I don't.
Right. because effectively the way this TCP works is it's really, because of its same channel parameters in /0 or J3161, it's essentially kind of a scavenger class of traffic that it's best effort when available and when there's not high vehicle density or high RSU density of traffic. So as far as construction zones and other things, this could be used for like the probe data upload, but it's not something you want to count on having in a timely manner or with low latency or high penetration. So it certainly could be explored, but it does have some pretty serious limitations. One of them is the percent of the bandwidth that's allowed to be used without interfering with this BSM is a pretty low threshold. So it's just enough to do some of these basic SCMS functions and some probe upload or CRL download or misbehavior reporting. I'm not really seeing this to well, I guess to be fair though, that even some of those flows aren't exactly defined in J2735 or J3161. So that this TCP traffic we're talking about is actually never 2735 or 3161. So this probe upload, for example, that's 2945/C, or this SCMS traffic, those could be proprietary protocols, or they could be CAMP standards or 609.2, but they're not SAE in definition today. So yeah, it is used for non 2735 and non 3161/1 messages. But the TCP flows still need to be constrained by that /0 channel configuration, that J3161/0 channel parameters.
So we've got a question here. It says the convention for BSM range is generally 300, but in your simulation you use 250. Can you explain the 250 as opposed to 300?
We will. I mean, I think because of path loss model that the simulation was being used, but we can certainly get the detail later on to address this.
I might have to get back to you on that one. The thing that we probably could stress there in that case though, that's kind of interesting, and why we looked specifically at that case where it was kind of a light channel load, with 50 vehicles and light number of roadside units, is that's the case where you're just on the edge of even being allowed for this IP to traffic to flow. If you had any more vehicles or any more roadside units, the CBR would be above that 30% threshold that /3161 defines, which would essentially nix all IP traffic. So this is the area of most concern, the worst case, corner case, that you have to make sure you understand the impacts at the CBR, where IP is just barely allowed, and then contributing the maximum allowed IP can contribute. And so you can kind of look at those curves and interpret where you would expect the 300 meter performance to change, and it would have a small, hopefully acceptable degradation. But it's not totally free, but it's also reasonable. Who had that question? Is that Anthony? So we can get back to him on the reason for the 250.
That is Frank.
Frank. Oh, Frank. Yeah, good question.
Okay, so let's see. That one's answered. There are current deployments where a file can be spliced into multiple UDP packets and broadcast it using link local IP version 6 and DSRC. Is something like that possible with this proposal? I'm assuming that the answer is no, because the proposal only supports TCP.
No, it's possible. I mean, it definitely supports UDP as well.
Yep. We just focused on TCP in the discussion, but absolutely UDP works identically. And in fact, as I think UDP broadcasts can be quite useful for the dissemination of things that are the same information that multiple devices need to receive, like CRLs. yeah, for bandwidth spectrum efficiency, that has the same function as it would in other radios.
What advantage is the approach to get OBU IP version 6 address different from using EUI64, using 48-bit MAC, add an FFEE 24-bit that is commonly used in IP version 6 stateless configuration? Stateless auto configuration, it says below.
Yeah, one of the interesting things, and this is similar to how it works in DSRC, the trick here is that for the unicast MAC link on this PC5 mechanism, you still need those lower 24 bits to generate the unicast MAC layer PC5. So for the addressing with that 609.3 unicast, it needs to have those 24 bits to translate the IP address into the layer 2 destination address quickly and without having to maintain a neighbor cache or peers or dedicated ARP tables. So this allows it to just be quickly converted from the IP address to the destination MAC for unicasting. I think that's the biggest advantage of why we're using that 609.3 address formation. I hope that answers the question. We can continue to maybe exchange emails on this one or set up a dedicated meeting.
And I'm muted. So I have, what advantage is the approach to get OBU IP version 6 address different from using?
This is the same one.
Same
Oh,
question.
same one.
Okay, let's see. I pushed done. Let's see. Okay, let's going down back to Roger here. SAE J29453 introduced percent of respondents inside the PSC field of the WSA to limit the number of OBUs that can connect to the cloud to reduce congestion. Maybe we can adopt something similar to reduce number of OBUs that can attempt the connection.
Yeah, absolutely. That same approach could be used. So go ahead, Lei.
No, I'm just
There's also some additional parameters that 2020 version of 609.3 brought in that also can be used similar to limit the number of connections. As well, the server could also just limit the number of connections for a given vehicle, but that for given roadside unit. But that's maybe a little trickier to implement. But absolutely, the percentage of responders is quite valuable, and we probably should have put that right in 609.3 actually in the wave router advertisement for the PC5 extensions. There are some fields in there that are the minimum range physically from the wave service advertisement 2D, 3D location that the connection can be attempted. There's a maximum speed below which you're not supposed to attempt to use that wave service, regardless of whether it's IP or any application. There's also some additions in those 609.3 extensions for the wave service advertisement for services that are just along those lines of percent responders. But I agree, percent responders in the wave service advertisements would be ideal. And maybe SAE specs like J3161 could propose that to help improve the network quality, because effectively what'll happen is you'll get, if you try to have too many percent responders, the available bandwidth will just produce poor link quality and low throughputs. So it is better if a few vehicles can complete their transaction and let others get their turn after you're done, rather than have a whole bunch of vehicles that just get a little bit of slow performance for the kinds of applications we're talking about, which is misbehavior reports, probe uploads, cert top-offs.
Well, it looks like we have a comment, and just for the benefit of the group, I will read the comment. Thank you for answering my question. In ideating how to inform L4 and L5 autonomous vehicles of a dynamic zone having safety critical conditions like VRUs, With intention of helping the AV make safer tactical maneuvers based on sending it increased knowledge, we're wondering how we can send data V2I to an AV. The TCP over CV2X seems promising, but understand if that's not on the roadmap today. And it says, thank you for a great presentation. But so thank you for that comment.
You know,
Any thoughts that you'd like to lend to that, Sean or Lei?
I think that there's lots of proposed messages and systems in SAE and at CITS that are working on that problem. And I think the approaches are typically not IP based, in particular because this IP traffic is, again, not the most efficient. It has a large overhead per packet. So for things you're sending frequently, that's one of the reasons we love wave short messages and that we use for our BSMs and our wave service advertisements and everything. But the things like sensor data sharing and cooperative perception messages, those can be done here with broadcast or with and that way all the relevant parties that might be interested in that information may as well receive that, rather than having them be specific peer-to-peer links, which is kind of the same approach we take with BSMs for now. Okay.
Well, we have one last question and 4 minutes, so this answer should be fairly short, hopefully. TCP is bidirectional with error correction, but this sounds more like UDP best effort. Is that more of a comment, I guess?
I would say
no, not really. No, not really. This is the standard TCP, yes, with error, whatever error correction the TCP supports.
Yeah, TCP, the timeouts are the same as they would be on any TCP.
Yeah.
The retransmission,
timeout, ACK, whatever. It's all there. It's all supported. Standard TCP. It's just the radio, the physical media. It's different. Okay.
Which this physical media does have is where the actual error corrections and
it's its own, radio layer thing. But I mean, if you're talking about the TCP layer, everything is standard compatible thing.
Yeah. So if you receive if a packet gets lost, the retransmission works the same way. The packets are ACKed at the TCP layer the same as ever.
Exactly.
And in fact, we're not proposing any different parameters, I don't think, for any of the TCP as far as congestion algorithms. At these low loads, there's not much. I think, Lei, you looked at a lot of different available TCP tuning parameters and discovered that the default standard network parameters are as good as anything.
I mean, the point is, this is the standard TCP, nothing special about it.
Yeah.
It's different.
What makes it best effort, and why I was bringing that in, is we're not talking about the network layer, but so much the PHY. So the equivalent of like the EDCA parameters on Wi-Fi, or the quality of service parameters. That PPP8 that we're talking about, that's effectively like the lowest quality of service. So like background data, which means that it will not be sent. It won't even put energy into the radio channel if it's exceeded its bandwidth for the small window of evaluation that it considers in 3GPP. And any other priority packets will preempt it. So that's what makes it sort of a best effort. But it's still, the data TCP will still fight through it. And as long as there is a period of time on the channel where the channel busy rate drops below that J3161 CBR threshold where PPP8 is allowed, packets will go through. Retransmissions and everything.
Okay. Well, we are at the end of our time. Lei and Sean, thank you so much. I know we spend a lot of time together in working groups. I appreciate your taking the time to do this with us here today for our members, guests, and friends. To our members and guests, thank you as well for joining us. If you have any questions regarding the presentation, membership, or even just general information, please send us an email at info@omniair.org. I will see you guys all later. Thank you so much and have a great day.
Thanks, Berkenda. See you at Plug Test.